Section 11.1 is functions of several variables, and in fact, chapter 11 is going to be calculus of functions of several variables. So this just introduces the definition of a function of two variables. We'll see the definition of a function of three variables with a couple examples as well. And it works on some of the algebra involved. So a function of two variables is a rule that assigns a pair of real numbers x, y, which is a subset D of the real plane, R2, some unique real number denoted f of x, y on the real line. So some real number off the real line. D is called the domain of the function f. Its range is the set of values that f takes on the real line. Okay, a diagram of this is down below. We have our domain D, some point f of x, y, and f is a map taking this point f of x, y to some point z, some number on the real line. So we've denoted somewhat generally the range of the function f is just some subset, open intervals, closed intervals, or even much more possibly complicated sets on the real number line. And this is just the basic idea of what this function of two variables mapping to the real line looks like. From R2 to R. One of the first tasks we'll need to be able to do is to evaluate such a function. F of x, y equals x plus the square root of 4 minus y squared. Well, evaluating is as easy as evaluating a function of a single real variable. So we have f of 3y, and we plug in 3 for x, 1 for y. Simplify the expression to get 3 plus the square root of 3. That's just evaluating the function at a point x, y in the plane and getting a real number, 3 plus root 3. Now, next question. They ask us to find and sketch the domain of f. So we look at the multiple parts of f, and namely we have x, and then we have a separate expression for y. And it's kind of lucky that that's the case. It won't always be this straightforward. Most problems will be, but you really have to kind of tease out what information you need from these situations. So what we'll know, and this process, this example covers the general process of this. So what we'll know is that x is unconstrained. It occurs as just itself. It can be any real number. So any x value is fine on the entire real number line. So that's good. On the other hand, we know that this expression 4 minus y squared has to be greater than or equal to 0 because it occurs underneath the radical. So once we solve for y in this situation, we've got y has to be between -2 and 2 inclusively. And that region is essentially a strip on the plane R2. So any x value, so it continues indefinitely left and right, to the right and to the left. And the y values are confined between -2 and +2. And that's more or less what we've sketched here. It's shaded in with diagonal lines, and that's our region. So to sort of put it all together and better than a sketch, we would say that the domain of this function, f, is equal to the set of all pairs x, y, such that x is in R, y is in R, and -2 is less than or equal to y is less than or equal to 2. And this is a decent way to close that up. So barring the line break in it, that's a nice representation of the domain of f using set builder notation. Find the range of f. Well, again, there's no catch-all rule for doing this. But in this case, if we let y be equal to 2, then we'll zero out the radical component of this expression. And all we're left with is an x. Well, if y is 0 and we just have an x value for our f of x, y function, something that looks like this, and we recall that a function g of x equals x has range all real numbers, well, so will f of x, y if it's equal to x. So it meets all real numbers, -infinity to infinity, and that's the interval notation for that one. So if f is a function of two variables with domain D, then the graph of f is the set of all points x, y, z in R3 such that z is equal to f of xy and xy is in the domain D of the function f. Okay, this is exactly the same situation we've always done with functions y equals f of x, single variable functions. Recall that y equals f of x is a single variable function. It involves the independent variable x. F takes x as an argument and y is the output. What that required in one-dimensional calculus was an x-axis and then a y-axis to mark the output of the function. Now, since our points occur in the plane, x and y in the plane, we have a third point, a third line that needs to be involved, and that's the z-axis. That's our output from points in the plane. That's what puts this function output in 3 dimensions. So any graph we make of a two-variable function from R2 to R is going to be a 3-dimensional object, a surface, essentially. Find the domain and range and sketch the graph of the function f of xy equals 1 plus 2x squared plus 2y squared. Now, first the domain. Well, this is polynomial in x and y. And just like a polynomial of a single variable, polynomials will have all real numbers as their domain. So it's as simple as that for this situation. The range of f. By inspection, we see that the smallest x and y can ever be in terms of their own expressions is going to be 0. Any negative numbers will result in a positive because they're both being squared. So the minimum output of this function f of xy is 1. And also by inspection, set y equal to 0 if you like, and then range x from 0 to infinity, and you'll see that the range of this function will go from 1 to positive infinity. There's no upper bound on this function. Or do the same thing, set x equal to 0 and let y range to infinity. You'll achieve the same range. Now, in terms of graphing this, what we want to do is perhaps check the traces. We know that, well, first thing to do is to let z be equal to f of xy, and that's what's happening right here. Z is equal to f of xy. In fact, this function is, as it's written, is missing some coefficients. It really won't be a big deal, as we'll see as we progress. When z equals 1, this is still correct, right? When z is equal to 1, the point 0, 0 is what occurs on the graph. When z is equal to 2, it's just a circle, okay? When z is equal to 2, in fact, it looks something like this. 2 is equal to 1 plus 2x squared plus 2y squared, and we'll see that bringing the 1 over, we have 1 is equal to 2x squared plus 2y squared. Dividing by 2, we'd have 1/2 equals x squared plus y squared. That's a circle with radius square root of 1 over 2. Okay, so anyway, horizontal traces, in other words, traces parallel to the xy plane, are circles. Okay, so that takes care of horizontal traces, circles there. In the yz plane, we fix x equal to 0. That gives us a parabola. In the xz plane, we'll set y equal to 0, also a parabola. We have two parabolas, one circle. We'll call it an elliptic paraboloid. You could maybe call it a circular paraboloid because the ellipse just happens to be a circle in this case. Drawing that, we have that point 1 right here at x equals 0, 0, and that's coming from this right here. And the rest of it, we know we have circular cross sections. That was from perhaps work like this. And we know that overall it's a parabola and the other traces, the other slices of it. So the elliptic paraboloid for this situation. And the graph of that function is as such. Okay, level curves of a function. Since it's generally going to be more difficult to graph one of these R2 to R functions, these functions of two variables, it's much easier to sketch the level curves of a function. And this gives us a decent idea of what this thing looks like without going through all the work of trying to draw a surface, which is a 3-dimensional object, on a 2-dimensional page. So the level curves of f, we just find all the variables x, y, such that the output is equal to k. So in other words, fix a constant value for the function and find all the xy variables that satisfy that. That is a curve in the xy plane, and we'll sketch that. Then you'll label that curve with the z value that with the constant k, or the z value that comes out from that space. So we're given a function. We're asked to sketch the level curves for this function. Okay, it's f of xy is equal to square root of 4 minus x squared minus y squared. Well, so we'll just start by setting this function f, or z, equal to 0, and seeing what comes from that in terms of equations. This is a circle with radius 2. Okay, so we could note that. That's actually sketched right here. The circle of radius 2 occurs when z is equal to 0. Every point on this circle yields 0 when it's plugged into this function right here. Okay, so that's the level curve for z equals 0. Z equals 1. Simplifying that, we get x squared plus y squared equals 3. In fact, if we do z equals -1, we get something similar. X squared plus y squared equals 3. Those are the same circles. And it is represented right here, marked with z equals 1 and z equals -1 if you zoom in closely to see it. Now, when z is equal to 2, we get x squared plus y squared equals 0. That's just a point. That's the point 0, 0 for x and y. Same thing for z equals -2. So that's marked as well as just a point, or a trivial level curve in the xy plane. Any value from that point, of course, is going to result in z equals plus or minus 2. Now, there are many more level curves that would fit into this, right? Technically, there are infinitely many level curves that are circles that are going to be centered at the origin like this. We don't want to draw them all. You just kind of pick some arbitrary values to go with. If a problem suggests a value, certainly find the level curves for that value. If not, generate some that are easy to work with. 0, 1, -1, those are all easy things to work with. Note that if we try any other values, z equals 3, for instance, resulted in x squared plus y squared equals -5 once we simplified the equation that results from z equals 3. Well, there are no xy values that satisfy that. This is an undefined situation. There's no level curve to go along with that. And actually what we realize is this is sort of our stopping point. We can't go outside of plus or minus 2 in coming up with these level curves, because anything that we do will result in an undefined situation. So this pretty much sums it up for building those level curves without any prompt on which values to use. Okay, so the next example below begs us to look at, or brings us to what the idea of level curves is sort of begging us to think of, and that's a topographical map, or a topographic map. And this example is asking us to look at a topographic map of our local Mount Charleston, and to find a trail called Trail Canyon, which is just east of Charleston Peak, and then assess the steepness of this trail from the contours of the map. So it turns out that a topographic map, and this is stated up here, uses level curves to represent elevation or changes in elevation in the map. Level curves that are closer together represent areas of steeper terrain. So let's have a look at such a map of Mount Charleston. And here we are. Trail Canyon is down at the bottom left here. This would be the trailhead of this area. And most of us have seen a topographical map before. If you look, you see lines parallel or more or less parallel to each other. These are all level curves. Some of them are labeled. Some values can be inferred from the labelings. We have 8,200 feet right here. This is telling us that if we were to stay on this line, we would remain at an elevation of 8,200 feet the whole time we were on that line. So we wouldn't go up or down. It would be easy walking if there was at least a flat path there. Otherwise, we're walking on the side of a hill, which could be cumbersome. But we wouldn't change elevation up or down. It wouldn't cause us it wouldn't tax us physically in that regard. Okay, so we can assess the steepness of this trail. It starts about right here, and it looks like between each of these level curves, we've got 5 gradations up to the next one, and that makes 200 feet. So it looks like it's 40 feet per faint line level curve that we see in there. So if we count down from this 8,000 feet where we're starting in the trailhead, we have 1, 2, 3, about 4. We'll say 4, so that's, what elevation is that at? That's 4 times 40, is that gonna make sense? Yeah, 160 feet, good. Okay, so we're 160 feet less than 8,000 feet. So at the trailhead, we appear to be at 7840 is where we're starting. And then Trail Canyon works its way in white along all of this. And we're just going to take it up to the fork. That's the termination of Trail Canyon, because this is the north loop to the summit of Charleston. So we'll stop right here. And what elevation have we gained? Well, if we look closely at contour lines here, we've got 1 and maybe about 2. We'll just call it 2 gradations down. So that's 80 feet below 9,400 feet. So that's 9,320 feet of elevation. So our net elevation gain for Trail Canyon here is 9,320 minus 7,840. And I'll let the reader handle the arithmetic on that one, but it looks like it's a thousand or so feet of elevation change, 1,500 feet, something like that. So it's a fairly steep trail, but you'll note that the trail does a good job of moving between wide gradations. So the further these lines are stretched out, the flatter the topography is in that area. If we were to turn to either side of Trail Canyon as we were hiking up it, it could get pretty miserable. If we looked up this way, these lines are getting closer and closer. To travel through that would be very steep terrain. Here would be even steeper. If we look off to the left, these would be cliffs moving along these, where these lines are so close together. So those are level curves represented by a topographic map. And if you didn't know how to read a topographic map, this is a nice lesson into that as well. So, lastly, a function of 3 variables. So very similar to 2 variables, only the domain is now in R3. It's in a 3-dimensional space. We'll pick a point X, Y, Z. We plug it into F, and it returns a value. I don't know, we could call it W, or in this case, we're calling it capital T. And if we're going to think about that, then what we might be doing is saying that for a point X, Y, Z in 3-dimensional space, T is the temperature at that point. It's a pretty easy thing to get a hold of in terms of examples. Now, just like mapping 2 dimensions to 1 dimension creates a 3-dimensional graph, mapping 3 dimensions to 1 dimension creates a 4-dimensional graph. This is not an easy thing to visualize. There's not really any way to draw it very nicely. And all we can imagine for 4 dimensions are slices, just as we've done to try to draw 3 dimensions on a 2-dimensional page. So that's really the best we can do. So what we'll do in this case is we'll talk about level surfaces, which are a lot like level curves, only the result of each one of these is actually a surface versus a curve. So we set the output equal to constant, just like we did for f of x, y, and then we determine what surface results from that in an equation of x, y, and z with a constant. So below, we set f of x, y, z equal to c, where c is some real number. Of course, we're given this function and we're asked to describe the level surfaces of it. So this is what we're dealing with. And we'll write that down below. We've got x squared minus y squared minus z squared equals c. Now, this looks like it's going to be some kind of quadric surface, but it's going to depend on the value of c. For instance, when c is equal to 0, so this slice of it in 4 dimensions, we get a cone in 3 dimensions. Okay? When we fix c greater than 0, You might think C equals 1. It doesn't settle all cases, but it's a good start. You might try a couple more just to convince yourself that C equals 1 is a good place to see that this is true. We get that the equation star here, star is here. This is a hyperboloid of 2 sheets. Okay, check it. And again, check it for C equals 1 to convince yourself. And when C is equal to -1, or sorry, when C is less than 0, and use your canonical C equals -1 for this case, star is a hyperboloid of 1 sheet. Again, plug in C equals -1 to star and see what form that makes, or reason your way through it, however you've come to identify quadric surfaces. So it's a messy business. There's not really one great answer to it, but I think we've successfully identified all 3 different types of level surfaces that might arise in the set of level surfaces of this function: a cone, a hyperboloid of 2 sheets, and a hyperboloid of 1 sheet. And there are going to be many of those. There are going to be infinitely many of those, because there are infinitely many choices for C greater than 0 and C less than 0 to make. So that's just a sort of a glimpse into functions of 3 dimensions, mapping to a single dimension. And that should wrap it up. There won't be too much focus on these harder versions, but the R2 to R1 functions, f of x, y equals z, those should certainly be mastered with this section. So that's it for 11.1. I'll see you in the next section.